Welcome to my project where I try to use CAN to model complex behaviors such as buckling in metamaterials. So first, what are metamaterials? Metamaterials are engineered periodic patterns called unique cells. Because of their design and structure geometry, their behavior is governed by local deformation. One of them is called buckling. This allows them to remain strong while remaining light and also to absorb much more energy. For example, they could be used to engineer new types of helmets. So my project will be about trying to build a CAN model that captures buckling. Here I have three metamaterials, so the Kelvin, the octet, and the simple cubic. The octet and the simple cubic exhibit buckling behavior. So and to do that, I first fitted a traditional CAN that was expected to fail. This will serve as a baseline to compare further models. Then I incorporated some non-monotonic activation functions to see whether I could help. In the same objective, I modified the loss to favor negative stress gradients. And finally, I relaxed the assumption that the weights of all activation functions should remain positive. So first, traditional CAN without regularization. As expected, it fails to capture complex behavior seen in the octet and the simple cubic metamaterials. Hence, I added some non-monotonic activation functions, so the swish and the mish activation function. Those functions remain smooth and less differentiable, which makes them really suitable for neural network learning. Without any regularization, we can see that those two new activation functions appear in the models, but they fail to capture buckling. And moreover, we have too many models, so let's add a penalty, an L1 penalty. Still, it's too far away from being satisfactory, so that's where I had decided to add a penalty loss that is aiming to favor negative stress gradient. So this will be denoted as R+. Even with a large penalty with the R+, it fails to capture buckling. So my final experiment was to relax the assumption that all the weights for the non-monotonic activation function should remain positive. It turns out that it did not help at all, so I think the whole strategy should be rethought. So in summary, CAN fails to model local deformation such as buckling, even when I'm relaxing assumption. So future work will be to maybe still use CAN but change the strategy, or maybe directly try with different other neural networks such as physics-informed neural networks or other type of PDE-based neural networks. Thank you.